Right, good evening again, CFSI CCNA class. Sorry about the mix-up earlier again. Um, I believe it was a network issue because as soon as I went downstairs and got a hardwired connection with this setup, everything seemed to start working a little better. Um, but we will probably stick with these pre-recorded videos, even though they kind of limit us in terms of in face-to-face interaction and real-time feedback for anything that you might want to ask questions, you might want to clarify immediately. The pre-recorded videos sort of limit us with that, but it does seem to give us a much better quality and much better content, just to cover the slides and cover the topics that you need to know. So I'll start over from the beginning for those who weren't able to see the session at all before or weren't able to hear me. Think of this as a full session. I'll cover everything everything we were supposed to cover for this class, and for the next class I'll probably do the same thing here. I'll record a video probably the night before and upload it in time for you all to view it at the same time you all would have tuned in for the real class. Okay, so let's begin. Everything seems to be working fine. My audio may sound a bit echoey because I don't have a studio quality mic yet, but we will see as the class goes on. We kind of improvising with the whole coronavirus right now. So let's see. Okay, let's see, back and forth. Right, good. So you should see these slides switching fairly quickly here. I noticed that was a problem with the Cisco WebEx session. These slides were, even at the best network quality, these slides were still a bit fuzzy and they took a lot longer. So you should be able to see these fairly clearly. Okay, so we'll start off again with the brief recap of the last class. We were able to get a bit of this in before the interactive session just died. But I'll still go through it for those of you who weren't able to see that even. And then for this class we'll be covering some interface and cabling issues, and then we'll be comparing two very important transport layer protocols, TCP and UDP. So Cisco specifically asked us to cover these transport layer protocols, but they did not ask us to cover any other protocol in depth, including the overall structure of the protocols in the protocol stack. So the OSI and TCP/IP model, they didn't specifically include that in their syllabus, which is better for you because it is a lot to learn and memorize, but it is sort of required. So you'll see I linked a video in one of the slides just to give you the same kind of understanding I did last week or the week before. With all the layers and what the different layers mean and how the layers interact with each other and that stuff. And from that we could dive into what's the difference between TCP and UDP. And then in the next class we'll get into IPv4 addressing and subnetting. So these are topics 1.4 and 1.5, these two, and then 1.6 we'll get into on Thursday. Okay, cool. So first, a brief recap of the last class. So what we did last week and the week before. Well, in this slide I just have last week's classes. Week before we did some basic infrastructure devices, so the routers and the switches and the access points and the basic rules and functions that those things serve in the network. So make sure you understand that. And last week we discussed how we arrange these infrastructure devices on the network. So the way in which devices are arranged on the network, if you recall, that is called the network topology, which simply means the manner in which our various network components are arranged. So whenever you hear topology, just think the way in which we string up our things together. So I have a short quiz here, so you could go ahead and pause the video once you, if you want. List at least two of the popular networking topologies that you remember and draw a small sketch of how components can be arranged in them. So of course you will pick your own devices and just get two of these and two of the topologies that you remember and make a sketch of them using some devices that you remember. So pause the video now and see if you can remember any popular topology that we discussed that Cisco wants you to know, and make a quick sketch of them. Okay, so you should have had some sort of sketch at this point. So I'll just go over some basic ones quickly. We already discussed this in the last class. So we discussed the two-tier model, which is just a model consisting of some small switches at the access layer. So these will be your small 1U devices, the same kind of switches we have in the class there, if you remember. And these will connect directly to end devices. And then on their uplinks, these uplinks may be copper or fiber, depending on how long the link needs to be and how much capacity we need on these links. And these uplinks will connect to the core or distribution layer. Now in the two-tier model, the core and distribution layer is in the same layer. So you see 1, 2. So in the second tier, you have that core / distribution layer of switches. So you'll see all of these access switches here connect into that core / distribution layer. Now we can expand on this with the three-tier model. So three-tier model, we still have this access layer here, which consists of these small switches, and you can see here we have the end devices directly connected. And then we have, from this access layer, we go up into just our distribution layer now, which may be layer 2 or layer 3 switches. And then we go up into our core layer. So we have a third layer that we add in here, which will be straight layer 3 switches or routers. If we need the extra horsepower, we'll put in routers there instead. So the functions of the distribution layer, the distribution / core layer before, will be split now between the core layer and the distribution layer here. So of course this will cost more money, but it will give us a lot more power in the network. So those are the two very popular and the typical Cisco topologies. But we also have here the spine and leaf model, which is a new model that Cisco introduced in the CCNA in this version. And it is a very popular model now. So you'll see all of these leaf switches here are connected to every single spine switch, so that if we have a server here that needs to send data to a server here, the data just needs to go up and there, or up and there. So one hop, very consistent. And this design is very good for east to west traffic. So if you have servers here that need to talk to servers here, you'll see your traffic just goes up and comes here, and it is very efficient because of the fact that every leaf switch is connected to every spine switch. In a lot of the leaf spine setups as well, you'll have the spine connected to a core layer, which is just used to get traffic out. So in the rare case where you need to get traffic out to the internet or out to some other network in some other data center somewhere, you have that path available. It's just that the amount of links going out will be a lot less than the amount of links here going east to west. And of course there are other topologies. These were just a few that I listed. Now we also discussed several common physical interfaces and cabling types that you are likely to come across in the field. So you should be able to remember some of the common cabling types. Now when you hear cabling types, you may not be thinking of what I'm thinking about, because cable types can mean a bunch of things. So in this case, I'm talking about the physical composition of the cables, just as one way to differentiate cables. So I hope you can remember the two main materials that we use for networking cables. It is copper and fiber. So you'll hear that in Trinidad and anywhere in the world. You have copper-based networks and you have fiber-based networks, based on, of course, the type of material that the cables are made from. Now, what types of connectors and interfaces can you expect to find on the ends of each of those cabling types? Well, you could have a bunch of them, depending on which cable you're talking about. So for copper cables, you could either have RJ45 for twisted pair copper cables. So remember the little strands that we mentioned, where we had them twirled individually, and then you had to unstrand them and crimp them and everything. And then we had F connectors, we had BNC connectors for coaxial cables, and coaxial cables had a bunch more connectors, whereas we just had the RJ45s for the twisted pairs. Now for fiber, I have seen, from my experience, I've seen LCs and SCs, but there are also other fiber types out there. So you might see something called a MTRJ, a ST, a FC. You might see others out there, but the LCs and the SCs are very popular. Now that we've reinforced the material from last class, let's begin some new work. So this is our actual new work for this class. So this is where we were before we cut out this evening. So as engineers, we will frequently be asked to troubleshoot various issues that may occur with these important components of our network. In fact, from my experience, interface and cable issues occur more frequently than equipment configuration issues. So think about it. You change, well, in a production network or in a live network, or in a network that is working and that your staff is using day to day. You change configuration on that very infrequently. So usually in an enterprise, in a business, once the network works, it works. You don't typically need to make a whole lot of changes. So your configuration issues are going to be very minimal. If the configuration works one day and it doesn't change in the next week, chances are you're not going to find an issue with the config in the next week, once you don't make any config changes. However, interface issues and cabling issues pop up all the time. So you'll have people moving cables, you'll have maybe insects or rats eating the cable, somebody mashed the cables, some rack or something pinch the cable, sometimes SFPs or transceivers may overheat. So you'll see a bunch of interface and cabling issues pop up from time to time. So we must therefore be able to understand several common issues that may occur, as well as how to diagnose and repair these issues. So of course, because these are so popular, you'll get a lot of experience with this on the field, but just as a baseline, we'll go through some of these common issues. So we will first examine the issue of network collisions. So we discussed collisions a bit last class, but we'll go into them a bit more in this class, and we'll go into how we could diagnose them using our Cisco commands. So collisions occur when multiple devices in a shared collision domain attempt to transmit simultaneously. So we discussed this concept of a shared collision domain in the last class with Ethernet shared connections. So all devices called hubs extended collision domains between devices and exacerbated this problem of collisions. So a collision domain, again, is just any part of the network in which two hosts cannot transmit simultaneously. So if you have, in these hub networks, for instance, if you have two devices connected to two ports on the hub, and both of those devices try to transmit data at the same time, you will have a collision of that data on the line, because they have the same collision domain. Yeah. So our modern switches and routers create new collision domains in each of their ports, ensuring that this idea of shared collision domains is eliminated. So as you could imagine, this idea of shared collision domains got old really quickly. As the networks grew and grew, and we went from 1 and 2 devices on a network to 10 and 20, we realized we needed to be able to allow devices to transmit at the same time, because these collisions were just getting more and more worse and deteriorating the performance of our network. So we created these new switches and routers, and every port on a switch and every port on a router creates a new collision domain. So we don't have these problems of shared collision domains anymore. But back then, this is what it looked like. So you had station A and station B, so just two PCs, imagine. Two PCs on the same collision domain connect. So this could have been connected to a hub port here and another hub port here. And if they attempted to transmit data at the same time, it would bounce up here, and both of these transmissions would fail because they detected that collision there. So you see, this is another diagram here. So you have A and B transmitting. So A, well, the time goes down here. So A starts transmitting at t equals 0, and then B starts transmitting at t minus some delta here. And you see, at this time, because they have this shared collision domain here, as the data goes out here and reaches here, and B starts its transmission now, they're going to bounce up along this line. So you see, this data was coming here, and then B reached, and you have this red portion here, which is the collision at some time. So B stops data transmission and sends a jam signal. So there was a special signal called a jamming signal. At this time, B would send that jamming signal because it would have the data would be able to reach B quicker, and it would be able to detect that collision quicker, because you would expect that the collision would happen somewhere here. So B would detect the collision first and send that special jam signal, and it would send that jam all the way back to A. So you see the red propagates all the way back to here, and then A would stop the transmission as well. So both of them would fail in their transmissions, basically, because of that jamming signal. So this diagram shows the concept of shared collision domains again. So you see this H for hub. So we don't really have hubs in modern day networks, but just to explain the problem of the collision domains again, you had a hub but looked a lot like a switch. It would have ports, and if you connected stuff to its devices like this, all of these devices would be in the same collision domain. So this thing could happen with all of these devices here. And of course, if you put more ports on the hub, it would get even worse. So you see with a switch port now, SW switch, we have one collision domain here with one thing transmitting. I mean, the switch isn't going to be sending that much data unless the device needs to receive or transmit. So it's basically this device in its own collision domain, as opposed to here where you had, if this guy wants to transmit a lot of data, these two guys are going to be getting a lot of collisions. Here, this guy could transmit and receive as much as he wants. Same thing here. Same thing between the switch and the router. Same thing between the two routed ports here. They have their own collision domains. So as you can see, as long as you aren't deploying hubs in your modern network environment, and you really shouldn't be because these are very ancient devices, the problem of collision should be mostly eliminated because we use switches and routers now. However, issues with cabling or connectors can actually create these collisions still. So you'll see Cisco will say that they have collisions detected on the interface even if you don't have a hub on the network. And we're going to explore some examples of how that could happen. So Cisco devices allow us to monitor these collisions using the Cisco ILS CLI command show interface and the interface name. So I believe this will be the first presentation where I'll get into some iOS commands in the presentation itself instead of just in the lab. So you'll see these words in italics. I try to make them in italics as much as possible so you know this is a command that you can actually type in to the router as opposed to these just descriptive words. So for instance, if one of your interfaces on the switch is fast Ethernet 01, you could do show interface fast Ethernet 01, where fast Ethernet 01 is your interface name here. So that is an actual command that you can put in. So you'll see here, this is a output of somebody running the command. So you'll see this is a router and they did show interface Ethernet 0. So Ethernet 0 was an interface here. So they pressed enter here and they got an output like this. So if you want to test this too, fire a packet tracer, get a router or a switch, drag it into your space, and then do show interface and some interface on the router or switch. So you'll see something like interface is up, line protocol is up, and then a bunch of information, and then I highlighted the important information here because of course this is a lot of info. So I want to ease you through it and make sure you understand it bit by bit. So this is the command that we ran, and this was the whole output that it printed, but for now we are focusing on this. So at the bottom here you'll see some number of collisions, some number of late collisions, and then some number deferred. So this is what we are talking about. Even without a hub in a network, Cisco will say that they have detected collisions on certain ports. So what does it mean? The deferred counter tells you the number of times that the interface has tried to transmit a frame but has found the link to be busy at the first attempt. So you see deferred counter, deferred. So you see deferred, this is the amount of times it tried to transmit. So this is not typically a problem as it is part of the CSMA CD operation of Ethernet. So CSMA CD is basically the same thing we just spoke about, where if something on the network tries to transmit, something else would detect the signal and would have to wait and back off and detect that collision before they could try to transmit again. So the same thing we just described with collisions. Ethernet was actually designed to operate with these collisions because it was a fact of life back then when you had hubs. So this is not typically a problem. It is part of the operation of Ethernet. So for those of you curious, CSMA CD, the CD part stands for collision detection there. So it is built into Ethernet to be able to detect collisions. Now the collision counter tells you the number of frames that have collided on the shared Ethernet segment. So collisions there, that is the number of frames that have collided on that shared collision domain, basically. So that's the amount of collisions we had, which is why there. So since CSMA CD is built into the Ethernet standard, this is not necessarily a problem as well. So again, we have collisions on the network. Ethernet was designed with this in mind, so it is not necessarily a problem. It could simply mean that there are a high number of devices transmitted on the segment. So it could mean that we do still have an old shared collision domain on the network, and we just have a few collisions. So that is a fact of life. Now, although the Ethernet standard was built to tolerate collisions, it has set a maximum time to detect these collisions on the segment. So just in the standard, they have a certain amount of time where they say, okay, while we're transmitting, we expect collisions to happen within this amount of time, which is 5.2 microseconds for fast Ethernet. So any collisions that are detected after this time has elapsed is termed a late collision. So Cisco just says, after this amount of time, if we detect something else colliding, then that is not a normal collision, that is a late collision. So late collisions, you should see it here. So you see collisions versus late collisions, right? So late collisions can be caused by incorrect cabling, non-compliant or non-standards based hubs, or bad NICs in devices. So your NIC, your network interface card, is just a card on your laptop or your PC that provides a physical port that you plug in. So it could be your Wi-Fi card to allow you to connect to your Wi-Fi network, or your wired card to let you plug in a physical cable to a switch. That is what your NIC is. So these late collisions, if you see a lot of them, so you see we have 0 here. If we had seen, I don't know, 100,000 here, it could have been caused by incorrect cabling. So you can see if the cable damaged, like physically damaged, or the connector is damaged, or if we have non-standards based hubs, so a cheap hub that wasn't designed to spec, or if we have a bad NIC in our device, all of these things could cause late collisions, and it'll cause this counter to go up. That could be why, possible reasons. So your solution now could be to swap the NIC, or swap the cabling, or swap the hub. So excessive collisions are caused by transmitted frames from a device being interrupted more than 16 times. So you'll notice we didn't have excessive collisions here. Now excessive collisions can be checked using the command show controller and the interface name. So not show interface. You see, remember here we did show interface and the interface name. Now we're doing show controller and the interface name. So that's how we're going to check these excessive collisions. So common causes of excessive collisions include incorrect duplex settings, broken NICs, damaged cablings and connectors, or just too many devices on the segment. So again, if we have too many devices on the segment, too many of them going to be trying to talk at the same time, and we're going to have an excessive number of collisions. So you can have incorrect duplex settings as well. We'll go into what duplex is a bit more in a few slides. We could have broken or damaged NICs as before, or broken or damaged cabling or connectors, just as before. So we have to swap our NICs, swap the cabling, or swap the connectors. I'll show you how to fix the duplex settings in a few slides. And well, for too many devices in the segment, we need to either, the best advice now is just swap out the entire hub, upgrade to a switch, and get it down to one device per segment. Well, 2 devices technically, one PC and one switch port. So you see we run the command here, show controller Ethernet 0. So just like show interface Ethernet 0, we had show controller Ethernet 0, and you'll see right here excessive collisions. So see 0 here, which is good. Now another common interface and or cabling issue is the presence of input or CRC errors in received frames on a host. So we went on to another set of errors now, input or CRC errors. So the Ethernet standard allows hosts to validate every single frame that they receive on the wire. So basically on a wire you transmit ones and zeros. Everything in the digital world is ones and zeros. But at layer 2 we group these ones and zeros into something called a frame. So now every time a host receives a frame or this group of ones and zeros, it validates those ones and zeros. So it performs a mathematical function, and through that math it can detect whether one bit was off. Just one bit. It could detect many bits, but even if just one bit is off, it could detect it through that math. So they perform this validation by the use of a cyclic redundancy check, or CRC, which is a value or checksum that the transmitter calculates and appends to frames before actually sending the frames out. Once a receiver gets the frame, it then recalculates this CRC and compares its own calculated value against the value that the transmitter sent to look for any errors in bits on the frame. So basically all this entire process is when the transmitter has a message to send, he gets the message and puts it in a frame, and then at the very last bit before he sends out the frame on the wire, he will run this this CRC check. So it's as a value that he'll compute. So he'll look at all the bits in the frame and he'll compute this CRC value and then put it at the end of his frame. So he'll say, look, using all of these bits here, I computed this value. So when the receiver gets the frame, he will look at the bits that he gets in the frame too before the CRC, and then he'll compute it again. He will compute it using his own set of math, and he will compute his own CRC, and then he'll compare his own computed CRC against the CRC value that the transmitter sent. And in normal cases, both of these CRC values should match, right? Because if all the bits match, then when it puts it into the CRC calculation, the output should be the exact same as it was before. If the CRC values don't match, then the receiver knows something inside there was changed, and therefore something is off with that frame. So you could tell the transmitter, look, I computed my own CRC, it is wrong based on what you sent me in your CRC, therefore I am going to discard this frame and I want you to send it back to me. Yeah? Okay. So this is what it actually looks like. So you have your Ethernet type 2 frame, so this is what a frame looks like. Typically you'll see your Ethernet frames could be 15 1/8 bytes. So this is how many bytes of data we could put on the wire. And of course we have very useful information in this frame. So we spoke about MAC addresses before and what they are used for. So they are used to get the frames around and used to address frames at the layer 2. So we actually need bits of data to address the frame, and the ether type to tell us that we are using Ethernet type 2. And then we have data from the higher ups. So this is just at layer 2 what headers we have. The data will be IP data, or if you're using a WhatsApp message, this will actually contain our WhatsApp message, our hey what's up, or hey good evening, that kind of stuff that will be in the payload. And then after all that, we will slice off here and we will compute our CRC checksum. So you can see this is one example of a value that may have been computed, but all it is a mathematical function. So it says, okay, take all these bytes of data and run, some addition, some multiplication, some division, whatever it is, and then at the end you will always get some data of this 4 bytes length, and you're gonna put this at the very end of the frame, and then the receiver will get this, chop off this bit and ignore it, look at all of these, run the data through the same mathematical function and compute this, and then he will say, okay, look, my CRC checksum was this, your CRC checksum was this. If it's the same, great. If it's not, discard that frame. So we can check for CRC errors on our Cisco device again by using the command show interfaces interface name. So same command as before, show interfaces Ethernet 0. And these CRC errors would be the same thing we discussed before, where the CRC values weren't exactly equal. Now, in addition to CRC errors, this command will show us a category of errors that Cisco refers to as input errors, which includes runts, which are frames that are too short or less than 64 bytes, giants, which are frames that are too long, more than 15-18 bytes, ignored, which means that they have no buffer space available on the interface, which means that the interface had no space to take in a frame, or just overrun, which means that too many frames were received simultaneously. So if you just keep sending data to a host and the host can't physically process the data, it will be overrun, obviously. Excuse me. Right, so show interface GI01. So you'll see we actually have some errors here. So you see input errors, this amount of CRC errors, frames, overrun, and ignored. So you see we have a bunch of these errors just logged here. So usually your complaint will come in as something higher up. So a user might say they can't browse, or their calls are very choppy on the network, or something like that. And these are the commands that you'll run at the layer 2 level, so at the switching level, and you'll basically be checking for these types of errors. So these definitions, you can come back and reference them in these slides. So if you want to know what an input error is, we have these input errors which group all of these things. If you want to know what a CRC error is, you can remember it now. Well, you know what a CRC error is now. So you could take note of that and you could explain it to your engineer. You could say, look, I'm seeing input errors on this interface, and this is what I believe is that error. Yeah? Now, these errors are usually caused by excessive electrical noise, or EMI, electromagnetic interference, on the wire, or it could be caused by damaged cabling, improperly crimped connectors, improper cable design. For example, running cables above their rated speeds. So if you if you remember the speeds from the last class, we went into the categories of cables and we said, okay, look, Cat 5e could run at this speed, Cat 5 can't run at this speed, Cat 6 could run at a certain speed, Cat 6e could run at a certain speed. And if you try to push them above that speed, you'll start seeing these types of errors. So this just shows you an example of the effect that noise could have on your signals. So this is what your signals might look like physically on the wire. So it's a voltage, you're transmitting volts on the wire because it is an electrical conductor, and this is what the signal looks like if you graph it out. And then once you put noise on the wire, this is what the signal looks like. So you can see we may be able to make out certain parts, but then certain parts become a lot more difficult to make out. So the end result is that bits are flipped. So if you look at the bits here, you'll see that certain bits may not always line up to what we want. Let's see here. Okay, well, the bits are actually the same because this is the send side, but on the receiving side they may not get these exact bits because you see the signal is all wacky there. It may understand a 1 to be a 0 or may guess a 0 to be a 1 because the signals aren't perfect there. So CRC and input errors may be resolved by replacing cabling and connectors using shielded cables or just using fiber cables, which don't need to be shielded, or moving cables away from the sources of interference. Yeah, so remember that we talked about shielding and how grounding out cables could protect us against a lot of this electromagnetic interference, or we could just move to fibers, which just don't suffer from EMI at all. So we could use this if we start seeing problems like this on our network. Okay, so now I mentioned duplex before, so let's get into what duplex really means. So duplex refers to the method in which two nodes communicate on an interface. So it's the method. In a half duplex system, an interface does not send while receiving or vice versa. So the system could send and receive, it just can't do both at the same time. So half duplex means you will not send while receiving, or you will not receive while sending. So yeah, like a walkie-talkie. So you hold on the send button and you talk, but you can't hear what they're saying on the same time, or you let go and you receive, but you can't talk at the same time. So it's one way, but they can't do both. In a full duplex system, a system can transmit and receive at the same time. So this is what we are accustomed to today. You could transmit on certain wires and you could receive on other wires at the same time. So both sides must always agree on the duplex configuration. Generally, all modern equipment uses full duplex. So that's what I'm saying. Modern equipment, we are accustomed to full duplex. We typically don't want half duplex anywhere in our network. So the duplex of an interface can be set with the duplex full command under the interface configuration. So when I say under the interface configuration, you'll remember where you could go config T and go into the configuration mode, and then you can go like int fa0 or int anything, and you can set configuration parameters for a specific interface as opposed to global configuration. This is what the duplex full command, where the duplex full command should be entered. So for instance, you'll type conf t and go into the config mode, and then int fa01 to go under fastnet01 that interface, and then type duplex full to force that interface into full duplex mode. So you'll see here config t and press enter, so you'll get here, then int fa01 to go under that interface, and then you can set certain parameters for that interface alone. So you could set speed 100 to force it to 100 megs, and then duplex full to force full duplex communication on this interface. Then to verify, of course, you have to exit. So you have to exit from here and exit from here, or you could type end. I don't think I had that in lab, but there's a shortcut. Yeah, you have shortcuts all the places in Cisco. But just to keep it simple, type exit here and then exit here, and you'll get back here with all the config in the brackets there, and then you could run your show commands again. So you could run show interfaces fastnet01, and you'll see here, right? So you see full duplex, duplex full, and 100 megabits per second, 100 megabits per second. So you can see we put in the commands and it actually followed it here. Now lastly, the speed or bandwidth of a link determines the maximum throughput or speed that can be achieved over it. So this is just how many raw bits per second we could push over the network. So you'll see providers quoting speeds a lot, 40 megs per second, 25 megs per second, 60 megs per second, 100 megabits per second, wherever it is. Well, whatever speed they quote, of course their links need to be able to support that speed or higher. So you could have a physical link that could support, let's say, 1 gigabit per second, but then the ISP could limit it to something smaller, but never anything larger. So if the link supports 1 gigabit per second, they could limit it to 500 megs, they could limit it to 100 megs, they could limit it to 25 megabits per second, as long as that link could physically support something higher than what they limited to. So different interfaces on equipment support different speeds. Many interfaces support multiple possible speeds. For example, a tri-rate interface may support 10/100/1000 megabits per second. So you'll see this in lots of equipment. It doesn't just have one speed that it could support. It supports something else, well, a few other speeds for backwards compatibility. So the reason for this is so that it allows you to upgrade your network slowly. So imagine you have 100 meg switches that could only support fast Ethernet speeds or 100 megabits per second interfaces, and then you want to upgrade to 1 gig. If you didn't have these tri-rate interfaces, you would have had to literally buy a replacement 1 gig switch for every 100 meg switch that you had before, because you couldn't make that link from 100 megs to a gig. You have to have a link where both sides operate at the same speed. So you would have to swap every single switch in your network at once, which is very difficult for a lot of businesses to do. So as opposed to that, with these tri-rate interfaces, we can run them at multiple speeds, and we could have, for instance, one port on a switch running at 1 gigabit per second, and another port on a switch on the same switch running at 10 or 100 megs per second. Now these interfaces usually negotiate the highest speed supported by both ends of the link, but sometimes cable damage, EMI, or badly crimped cables may cause them to negotiate lower speeds. So you might think that you run a cable, and between the connectors and the link, the cable and the interfaces, everything should support 1000 megabits per second, but for some reason the interface negotiated 100 megabits per second. So these things usually result in that: cable damage, badly crimped cables, noise on the line. I have seen all of these. So remember the tower example I gave a few classes ago. We had a Cat5, no, it's Cat6A cable running up a tower, and we had the proper connectors, we had the proper transceivers, we had the proper interfaces. Everything said the link should be operating at a full gig, but for some reason we always found that it would drop to 100 megabits per second, just intermittently. It would flap between 100 and 1000. And the problem was noise. We had that EMI because a bunch of other carriers were on that tower and they had their own cables on the tower, and of course the tower had wireless links, and all of those wireless links put noise on the wire as well. So because of that EMI, our cable was running at 100 megabits per second. So what we had to do was swap it out to fiber. We could have put shielded cables. Well, we actually had shielded cables, but it wasn't enough. The shielding just wasn't enough for all that noise, so we had to move to fiber, which fixed our problem. So in order to ensure speeds across Ethernet links, it's possible to statically set the speed using the speed command on an interface. So you go config T, interface, and whatever interface it is, so interface Ethernet 2.1, and then statically set your speed to speed 1000. So you could force your device to say, look, I don't want you to drop below anything below 1000 megabits per second. I want you to always operate at this speed. The problem with this is that if the switch can't actually negotiate this speed, or if it can't run at this speed, of course, because of the example I just described before, where you have noise on the wire and it just couldn't push that 1 gig per second at all, if you put this speed 1000, it has no way to fall back. It will never fall back to the 100 megs, so you will just see that your link is down. And if the device is out somewhere in a tower, of course you need to physically go and fix the configuration. So as an interesting note, while you can set speed and duplex configuration statically on both ends of the cable, equipment is generally fine at negotiating the proper settings for itself. So usually I've found that once you link any connectors and the cables and everything is fine at the speed that you want, it will negotiate it by itself. So an issue with auto negotiation is usually related to an issue with EMI, cable damage, improper connector termination, or some other combination of cabling and connector issues. So all of the times that I've seen this thing called auto negotiation fail, and you want it to negotiate as a gig, but it goes down to 100 megs, all of those times it's been some kind of issue between cabling and connectors, or damaged, or noise. So auto negotiation tries to tell you something, basically. Note also that different cabling, connectors, and transceivers are designed for different speeds. So of course we covered the cabling before. Certain connectors as well may not facilitate the higher speeds, and of course transceivers, or SFPs, as you'll hear in the field, they all operate at different speeds. So you'll have a transceiver that could only support 100 megabits per second, and another one that could support a gig. So a transceiver is basically this is a small device that you plug into a port on a switch or a router. So for instance, a fiber cable, you can't, you very rarely see a switch that you could plug a fiber cable straight into, like how we plug copper cables into a port. A transceiver gives us the proper termination so that we plug the fiber into the transceiver and then put the transceiver into the switch. So the transceiver could limit speed as well. So you may experience issues when trying to run above the lowest common denominator of your link. So if your cabling and the connectors say you can run at a gig, but the transceiver is 100 meg, you can't run it at the full gig because you need to upgrade your transceiver first. So we had this table a few classes ago where I showed you, for example, Cat5 is rated only up to 100 megabits per second, whereas Cat5e is rated up to the full gigs. The full 1 gig. Cat6 is rated up to 10 gigs, but only up to 55 meters. Where, yeah, this should have been 55 meters here at 10 gigs. Cat6e, yeah, this shouldn't be. This should be changed. The Cat6a should be able to go a full 100 meters at 10 gigs, and Cat7 as well. 10 gigs, 100 meters. Yeah. I've never actually run Cat6a at the full 100 meters at 10 gigs, but it should be able to, as far as I know. But anyway, at those speeds, people usually say just go fiber anyway. These cables usually give trouble at those high speeds, at those long distances. But the takeaway here is that different cables are rated for different speeds, so you will get trouble if you try to run a cable above its rated speed. So yeah, this is the equivalent for fiber. So you'll see single mode fiber rated for 100 megs or 1000 megs or 10 Gs at different distances. Same thing with multi-mode fiber. Different distances, different speeds on top here. So every cable has its rating for distance and for speed at that distance. So make sure you know this. Right, so let me see, I could pause here. Good. So I can take a pause here. Let me get some water. You can also pause the video and get some water and stretch your legs a little bit, and in like 1 minute I'll be back and we'll start our second topic for this class, which is comparing TCP and UDP. Right, welcome back. Okay, so we're about 43 minutes in. Good. Okay, so we just now that we understand a bit about the interfaces and cabling issues, let's move back to the OSI and TCP/IP model. So in this second topic for this class, we'll be shifting from the lower layer and physical issues, from interfaces and cabling issues, and we'll be moving up a bit into the OSI and TCP/IP models. Now, in this version of the exam, Cisco has eliminated these models as an explicit topic. So they actually don't mention the OSI or TCP/IP models anywhere in the exam topics. So I actually put the exam topics on the drive as a PDF. If you look through those exam topics, you won't see a direct topic listing learn something about OSI or learn something about TCP/IP. But it is relevant, of course, and it is actually essential to understanding TCP and UDP. So just because I don't want to talk about, well, I don't want to spend too much time on something that's not directly relevant to the course, for anyone who doesn't understand or have a basic appreciation of the OSI and TCP IP models, I linked another video here. I had one, I believe, in the first class, and I have another one here. I believe this guy did it the same way I did it in the class, just a general sketch and a big overview of how each of the models interact, well, how the models compare and how all the layers interact, and why we need to understand the different layers. So feel free to pause the video now and click this link here and watch his video. I believe it's around 18 or 19 minutes. So in my own words, both of these models basically allow us to categorize and classify different functions that have to be performed at different layers or levels in our network. So it simplifies our troubleshooting, giving us a logical manner in which to diagnose issues. So rather than examining the entire stack, we will only be focusing on the transport layer in order to compare the two most popular protocols at this layer, the Transmission Control Protocol, or TCP, and the User Datagram Protocol, UDP. So basically, to me, these OSI or TCP/IP models allowed people, well, a bunch of different people who are involved in the whole networking field to segment themselves. So it was very difficult to tell one person that they needed to understand every single thing about networking. They needed to understand the networking aspect of applications, and then how the apps are displayed, and how they communicate within a client-server model or other apps. They need to understand routers, they need to understand switches, they need to understand the physical links, they need to understand microwave links, wireless links, wired links, fibers, splicing, crimping, everything. It was very difficult to tell one person that they needed to understand everything there. So what they did is they came up with this model, or these models, that let us segment different functions in the network into different levels. So to build on that concept, we are actually going to segment the models as well, and we are only going to discuss two very popular protocols at one layer, which is just the transport layer. So we're not going to discuss protocols in the other layers yet. We're just going to discuss the two most used transport layer protocols, TCP and UDP. So in the whole networking world or internet world, when people talk about the transport layer, these are the two protocols that you'll see mentioned, UDP and TCP. And now you're going to understand why we'll choose one over the other. So TCP and UDP deliver very different services to the upper layers. TCP provides a reliable, in-order, connection-oriented service, while UDP provides an unreliable, best-effort, connectionless service. So in this section, we're going to understand what each of these words mean and why we care about them. But if we ever have to summarize, this is a very good summarization of the differences between them. These words capture the different services that they provide. So they are both used by a variety of applications depending on what the requirements of the applications are. They each have their own set of advantages and disadvantages, as we will explore now. So you may see, well, from what I've seen, TCP is used a lot more than UDP, but they both have a place in the modern internet world, or the modern networking world, and you'll see why. So this is a meme that's been going around a while back. This is what TCP looks like, and this is what UDP looks like. And after the next few minutes, you'll understand why. Yeah. So let's first explore the concept of a connection-oriented service versus a connectionless service. So TCP provides connection-oriented connections between machines transferring data. So what is connection-oriented and what is connectionless? So TCP provides connection-oriented. So TCP is on the side of connection-oriented. What is connection-oriented? What does a connection-oriented connection mean? Well, what does connection-oriented mean? This means that before machines can begin transferring data, they must first set up a connection between them. So basically, if A wants to talk to B, A and B must first negotiate some stuff and decide how they're going to talk. Basically, they need to build a road between them and then start transferring messages back and forth along that road. They can't just send out like send out a message immediately. So in TCP, this connection setup process, so this process of building the road between them basically, takes place in 3 stages. So you have step 1 is a SYN message or synchronized message. Step 2 is a SYN/ACK, so synchronize and acknowledge, and step 3 is a ACK. So you'll hear we'll talk about the TCP three-step handshake, and this is it. These are the 3 steps. So SYN, ACK, and ACK. Right. So this is the diagram showing how that 3-way handshake works. So you have your client and your server, and they want to communicate with each other. So if they want to use TCP, they can't just start communicating immediately. They need to set up this road between them using this three-way handshake. So you'll see the client actually started the connection here because he sent the first message. So his state changed. So he sent the first message, which is a SYN message, as we saw here. So step 1 is a SYN message. So SYN, and this SEQ is short for sequence. He has a sequence number of 100. We will explore why sequence numbers are important after, but for now, just appreciate that we need sequence numbers in TCP, and he will send his sequence number with this first SYN message. So he sends out this first SYN message, which means that he started this connection. So he basically said, look, server, I want to send data to you, so let's set up a road between us to send data with this SYN. So he sent this SYN message. So the server now got the SYN message. He changed his state to SYN receive because he received a SYN, and he's going to send a SYN/ACK message in return. You see, SYN/ACK, step 2. That's step 2 of this 3-way handshake now. So we went from step 1, which was the SYN message, to step 2, which is the SYN/ACK message. So he acknowledged 101. So he got 100 and he acknowledged 101. So basically, he took the sequence number and said, look, I acknowledge that you sent 100 to me. This was the sequence number, so this is just a random number that the client sent to him. He said, look, I got this number, and to prove to you that I got this number, I'm going to send an acknowledgement message, which just says, look, I got it. But he's not going to send the acknowledgement for 100. He's going to send 101, which basically says, look, the next number I am expecting from you is something with 101, because you just sent 100. So the next one needs to be 1 above that. And then he's also going to send his own sequence number, because this was, remember, this was the client's sequence number here. He's going to send his own sequence number so that the client can know his sequence number, which is 200 in this case. These 2 numbers can be completely random. They don't have to be 100 or 200. So that was step 2. And then step 3 is the ACK. So you see his state changes to establish. So basically the road is built now. The road is built between them, and they can start transmitting data. But of course, the third step needs to complete. So even though he changes his state to establish, he also needs to change his state to establish, and he will wait until he gets that third message, which is the ACK. So he will get that ACK message from the client, which says, look, I am going to send this message with sequence number 101 as you were expecting before, and of course I took this 100 and I just incremented it by 1 as I was supposed to do, and I am also acknowledging the 201. So you send 200 to me, I am acknowledging 201 to show you that I got this 200, and I'm expecting your next message to start with 201. And then you see both sides change their state to establish, which means that both sides could communicate with each other now. So we'll explore what the sequence number, why we need sequence numbers in a little bit, but basically for this, at least understand why we need to set up this connection. So you see, TCP is a connection-oriented service. So TCP provides connection-oriented connections, which means that before they can begin transferring this data, they must go through this process. All TCP communications, whenever they need to transfer data, they need to go through this 3-way handshake. And the 3-way handshake is always this. It's somebody starting this connection, and then somebody acknowledging the connection, and then acknowledging the other way, and then you have the 3-way handshake completed. So this is something that you need to know. I have been asked this in interviews, and I always draw a diagram because it helps me to remember these things. I may not remember these words perfectly, but once you could explain, the base concepts and why we need to set up these connections, you'll get points for it, so of course, in the interview. So appreciate the three-way handshake that TCP needs to go through. Now, in addition to simply establishing an open connection on both sides, pay attention to these sequence numbers. Sequence numbers are used to provide both reliability, which is ensuring that any data transmitted by one machine is actually received by the other, as opposed to being lost, and order, which is ensuring that data is provided to the receiving application in the exact order in which it was sent. So it's two things we're talking about here, right? Reliability, which means if I send you a message with the letter A, I need to make sure that you got that message with the letter A, and it didn't end up on the ground or in the bush somewhere. I also need to know if I send you A, then B, then C, you didn't get CBA or BAC. I sent it to you in a particular order for a reason, and I needed to receive it in that same order. So how does TCP guarantee this? How does it guarantee that a message that was sent actually got to the receiver, and how does it guarantee that the order in which it was sent is the order in which it was received? So TCP does this by the use of something called acknowledgements, which we just discussed. For every TCP segment that a machine receives, it must generate an acknowledgement message, telling the transmitting machine that it received the segment, and also letting the transmitter know of the next sequence number it is expecting. So these acknowledgements now support both of these functionalities. It lets us know that we got the message, and the receiver got the message, and it also lets the sender know that order was preserved because it received the packets in a particular order. So you see, this is what we went through before. So this is the progression of time before. Host 1 sends some data A with a certain sequence number, and then host 2 sends an ACK for a particular next packet or datagram. So you see that he got the sequence number with 46, so he's going to send the ACK of 47 to say, look, I got your 46, and to prove that, I'm going to send you 47, which means that I'm expecting your next bit of data to have that sequence number of 47. By keeping track of these sequence numbers, you can now see how TCP provides in-order delivery. If TCP segments were to pass through different parts on the network, the receiver could simply store the segments and reorder them before providing them to the receiving application. So what we're saying here is, if you send data and somewhere along the way, messages pass through different roads, the messages get split up, messages bounce back and forth, and they take different paths. Even if the TCP segments were to pass through different paths, the receiver could still collect all these messages and buffer them, which means just store all the messages in some bit of memory and look at these sequence numbers and reorder them. So just shuffle the messages around as they line up in increasing numbers. So the diagram looks a bit complicated, but it is fairly simple, right? So we have a sequence number of 1 and a sequence number of 1001. So you see sequence number 1 was sent through here first. So of course 1 comes before 1001. So 1 is going to be sent first. So you see 1 was sent here. This router through this link, this other router through this link, coming here, and then reaching PC1. But you see here is a slow route. So maybe this link is congested, and this sequence 1, this message with this sequence number of 1 got stuck here, or got stuck here, and he took a lot longer to reach here. Whereas the next message that was sent with a sequence number of 1001 got sent here, and this link was a lot faster. So you didn't have to wait in any queues or anything here. He just got sent. And because of that, 1001 actually got received before 1. So you see now what PC1 has to do is it needs to set up something called a receive buffer. So PC1 will say, look, I have this big bit of memory. I'm just going to store these messages, and I'm going to wait. So he'll say 1001 got here before 1, reorder it before sending it up to the application layer. So remember, the whole point of these transport layer protocols was to provide a service to the upper layers. So if, for example, WhatsApp was expecting this packet before this other packet, PC1 could now say, look, slide this in here, so like a puzzle piece, slide this in here, and then slide this in here, and then provide this entire thing up to the application layer in the correct order. So just in case you're wondering why we didn't go 1 and 2, this is actually realistic. So our messages go, so if you start with sequence number 1, you'll see TCP actually increment that 1, not go 1 to 2, but it might go 1 to 1000 or 1 to 5000, and the difference here is actually the length of this packet. So think of it as we started this packet with 1, so we put 1 here, and then we take the length of this packet, or the length of this datagram, and if it's 1000 bytes, we'll go 1 and then 1000, and then start the next one at 1001. So that difference there is the length of this packet. Yeah. So if this packet was bigger, we could have gone 1 and then 2001, depending on the length of this first packet here. We'll start the other packet as the sequence number plus the length of the packet. So if you ever do a Wireshark capture, you'll see that TCP doesn't do sequence numbers like 1, 2, 3, 4, unless the packets are actually 1 byte long, which is why I put the data was just A here. So 1 character may actually be 1 byte long, but typically you'll see much bigger packets in the network. You can also see now how TCP keeps track of lost segments. So if there's a gap in sequence numbers of the segments, then TCP resends the ACK up to the last segment that it received. So just another function of TCP, if host 1 sends 46, and then 50, and then 54, but host 2 doesn't get all of these, host 2 will send back an ACK for 50 or 51, saying that, it will send it back for 50, because it is expecting 50. You'll say, look, I got 46, and I got the whole length of 46, that was fine, but based on the sequence number here, and the length of this packet, I'm expecting your next packet, or your next segment, to be 50. But this died somewhere along the way, and then even though I got 54, I was still expecting 50. So he will send an ACK for 50. And now you will see how TCP is leveraging these ACKs to say, I am missing this data host 1, please resend it to me. So yeah, I was thinking of one other thing here. Oh, right, so just to mention, you'll see in the last 20 or 30 years, TCP has gotten a number of optimizations. So because TCP is so widely used, people have sort of revised the algorithm, so they make it more efficient, basically, because they expect these things to happen. So for instance, in one case you might think, okay, if host 2 got 54 but it didn't get 50, then just drop that and ask back for 50. But isn't it more efficient to now store 54 and just keep it in memory, so that when you get back this missing packet, you don't have to request 54 again, you just have it in your memory waiting. So you just reorder it and you take that whole 54 and you put it in the correct order. So that is one example of what TCP does. Another example is that instead of host 1 sending one message and then waiting for this ACK to send another message, it can send 2, 3, 4, 5, however many different datagrams. It can send out a flood of them and then wait for the ACKs for all of them from host 2 and then send out another flood. Because usually these host machines can send data and receive data a lot faster than the messages can be transmitted along the pipes. So remember, we have fiber going all the way from Trinidad, across the whole of Trinidad and the whole of Tobago, under the sea, going up the Caribbean chain, going to Miami, going through the whole of the States, going through Europe. So these packets could take a long time to get to their receiver. So because of that, it makes a lot more, we make a lot more efficient use of our time by just sending a bunch of them and waiting for those ACKs, rather than sending one and then waiting and then sending another one and then waiting. So now that you understand a bit about TCP, let's explore UDP. How long? 1 hour, right? So UDP provides a completely connectionless service. If a transmitting device wants to send data to a receiving device, it does not need to go through any connection setup process, as we saw previously with TCP. It just starts sending. So basically, instead of building a road between both devices, our sending device could just start sending a messenger or sending out the messages one time. That's what a connectionless service means. It doesn't need to set up that connection. So you see, if host 1 wants to send A, just as host 1 wanted to do before, it just sends A. It doesn't care about sins and ACKs and all of those madness. Just send A. Sending with B, just send B, just send C. So you save on time, because you don't need to wait for those ACKs and set up the whole three-way handshake and everything. Just send your data. So in addition, UDP datagrams also have a much smaller header, leading to lower overhead in packets. So of course, to get all that fancy functionality that TCP had before, we need space on that segment, on that TCP segment. So we need somewhere to store those sequence numbers, somewhere to store those acknowledgement numbers. And all of these sins and acts and all of those things were flags. So we need somewhere to store those flags. And the window size set tells you how much you could send, like how much a sender could send before having to wait. That's what that window size controls. So all of these nice bits of functionality require space in this header. So you see bit number, and we're going up 128. So all of these things didn't really contribute anything to the application. So none of this is our nice WhatsApp message or web page. It just takes up space in our segment, in our packet, and it is extra bits on the wire, which takes away from our speed over the wire. So you can see why we may not want this. You see UDP bits 0 to the 2. You see a lot. It's just this in there. You can fit 2 of these in there, and more, 3 possibly. You see how much shorter this header is, so we have much less overhead in this. So we make much more efficient use of our wire, basically. However, this of course means that we lose many of the benefits that we saw with TCP as well. Think of what happens if we lose or misorder a datagram now. Since there are no sequence numbers or acknowledgements involved, the transmitter has no way of knowing that the receiver missed the datagram. It simply keeps on transmitting. So remember we sent A, B, and C? Well, how would we know if B reached? We don't. We just kept sending. So host 1 has no way of knowing that the data B was never received. So host 2 just saw A, then it saw C, and both sides are none the wiser. They don't know that B was dropped. Therefore, as we stated in our opening discussions, both protocols have their own advantages and disadvantages. Now, based on your new knowledge of these protocols, what sorts of applications do you think would use TCP and which ones would use UDP? So think about the choice for the following categories or application layer protocols. So think about these things that we may do on the web browsing, transferring files, streaming movies, or online games. So I put some of the exact protocols that we use there, but just based off of guesswork. Make your best guess about which one you think we would use for each of these, TCP or UDP. So pause the video now and take a guess. So here's the answers. Web browsing, which is HTTP or HTTPS, uses TCP. So web pages need reliable transfer to ensure that all of their components are received correctly. So of course, if we put our credit card on Amazon, we want to send those numbers and make a purchase, we need to make sure every single digit in that credit card got sent correctly. We can't afford to lose a datagram or a packet that contains half of the credit card. It is completely wrong, right? So we need TCP to ensure that all of those packets are received correctly. Transferring files also uses TCP, usually. So we need to ensure that all parts of the file are received correctly. But there are file transfer protocols, not FTP, but there are other protocols that let us do it using UDP. It's just that we may miss certain parts of the files. Now live streaming video with RTP uses UDP. So we can't tolerate a few missing pixels of video, rather than continuously buffering and delaying live streams for hacks. So for live stream videos, you'll usually see UDP used because you just want to see that video as quickly as possible. You don't care, if you have some pixelation here, if you have a little black screen there, for half a second, you're really business. As long as you see the video quickly, and as long as you don't have, a 10-minute delay, a half an hour delay, because of that continuous buffering and that delays for hacks, basically. Same thing with online games. Many online games use UDP for certain functions, where it is important for all players to have real-time information about maps or real-time information about other players or whatever. So if you shoot a gun now, you don't want to have to wait 5 seconds for that to register on your other player's screen. Using that whole TCP overhead and that heavy ACK waiting system, you want it to be as quick as possible. So now you can understand why we have this picture for UDP and this picture for TCP, and this picture for UDP. So the concept for UDP is just send, just throw it. Wherever it reaches, some might reach in its mouth, some might not. the point is you just keep trying. Whereas TCP is a lot more focused and a lot more accurate, getting that directly into your mouth. Yeah, so you can see the joke now. Right, so that is it for today. Next class we will be going over IPv4 addressing and subnetting, which is a pretty heavy topic. So make sure you have a piece of a notepad, a piece of paper, and a pen. So we'll be drawing up some tables and practicing some subnetting one time. So I hope you all enjoyed this class. I think yeah, 10 minutes should be fine. I think this video is a lot better than the live stream. So let me know whether you all were able to follow correctly. Let me know if you have any questions, and let me know if you prefer this to the online interactive classes.